Hello everybody. So as we know that we are in the third part of the course, which is on testing, and now we are going to start the second module. That is, we have already seen the basics of tests of an embedded systems. Now we are that is the basics of the prerequisites we have already discussed, which is required to understand in depth of the testing of embedded systems. Now in the next part we are going to look at some of the concepts which are more specific to embedded system testing. First we are going to look at some kind of a fault models which are motivated from hardware software design, and we are going to look at testing at a higher level of abstraction. Then we will look at, because nowadays embedded systems are made up of multiple cores, that is, you do not actually make all the cores by yourself, you can import them from the vendors and put it in a large die, which is the NOC or an SOC. We will see how to test them, and finally all such complex embedded systems are connected by bus and memory. So we will look at bus and memory testing. So now we will start with the concepts on high level testing using the concept of software based fault models, because as we know from Professor Arnab sir's discussion, Professor Deka's discussion, that embedded system is lot of hardware and software co-design and co-verification. So what we have seen, that all testing are basically done with fault models, mainly stacked fault models, and we call it a structural test. So fault model is nothing but an abstraction of the fault, abstraction of the real defect, so that testing becomes very simple, and you can generate the test patterns easily. You can expedite test by applying test patterns fast, because the number of test patterns will be small, but at the same time there is a very good correlation between the fault models and the real defects, so that quality can be ensured. And then basically what we have seen, that we have already seen and details about stacked fault models, that what is the complexity there, that is, if the number of circuits nets or lines are n, there will be 2n the number of stacked faults which you have to test it, and basically many of the cases will require backtrack, that is propagation and justification side, that you have propagated a fault, then you have to justify it, so there may be errors or there may be conflicts, so you have to again backtrack. So that backtrack is basically one of the main complexity of the circuit. And in fact, in modern embedded systems, basically the circuit size, the number of gates are in millions, and there are multi-core designs. As I told you, an NOC or an SOC may have 1028 circuit cores itself. So even if you are, as we have discussed, the stacked fault model is very efficient, because I mean the number of stacked faults are just 2n, not exponentially high. Also the test patterns, for most of the cases, first we go for a random test pattern generation, and then for very difficult faults we go for sensitize, propagate and justify approach, where there can be conflicts. But if you think about very large and practical embedded processors, the number of cores are so exorbitantly high that even stacked fault detection ATPG becomes very challenging and difficult. So for such cases we require even a very faster method of test pattern generation. Again I am telling, this lecture is not to minimize the test patterns as such. That is one of the main criteria, of course, but main emphasis of or motivation of this kind of test pattern generation came from the fact that even stacked fault model based, such an optimized scheme for stacked fault model test could not be applied for large scale embedded processors. So there people have to think of something different. Stacked fault model based testing will work very well for mainly single core units, but when we have gone to ultra large scale integration for embedded systems, such type of things started failing. So then people started thinking, can I do something in the abstract level or in a more soft level? Because in embedded system design, first we generally have the software development, then you have a hardware partitioning, but then again the hardware is also written in a very log mode, which Professor Arnab sir have told you in brief. So basically embedded system have lot of soft cores inside or software level descriptions. So the idea people thought is that, can we have some kind of a hardware fault model, and RTL means register transfer level. Can we try to test circuits at a very high level of abstraction? Testing cannot be very at a high level of abstraction, because testing always happens in the gate level fabricated device. I should test plan, can it be developed at a higher level of abstraction? Because if you have gate levels and more finer details, basically what problem you are having is more number of wires in multi-core SOCs, extremely high number of gates and nets, and even with this very efficient test methodologies like structural test for stacked faults, this becomes very complex to handle. So people thought, can I plain test at a very higher level, and it should be possible in case of embedded systems, because embedded system many modules are written in a software hardware co-design methodology. So we have very high level description models for many of the systems. So most of the important issues of testing in modern deep submicron embedded system design is scalability, as I was saying of the multi-core systems, because test schemes are generally logic level leading to state explosion. To solve this issue, people tried to move it to a higher level of abstraction, like register transfer level, architecture level, etc. But again, if you are moving to test a higher level of abstraction, you should have very high level fault models for the embedded systems. Can we have a high level fault model? So that is the motivation of this lecture, that looking at the embedded system design from a software perspective and software models, what can we do? Before going to any elaborate theory, I will take you to an example. So this is an example of a GCD computing hardware. Assume that this is a embedded module with embedded soft hardware which will do GCD calculation, greatest common division. Again, in embedded system or in most of the cases, we also have a software description, because, and it is more emphasized in embedded systems, because embedded system starts with a basic software description. Then we take some of that soft codes and some will actually take as hardware. So always we have good deal of software description for such modules. So if you look at it, it's the same very standard algorithm. We take the inputs and then we compare V1 and V2. Whichever is larger, we do this subtraction. If V1 is larger, we do V2 minus V1, and otherwise we want V1 minus V2. We keep on doing it till basically till both of them become equals, and then the output is actually V1. Very standard algorithm. And basically it is the hardware circuit that looks like, but now it is described at a much higher level of abstraction. That is what has to be looked into. We will not go into gate level description. So if you look at it, I will just give you the description of the circuit, because it is more or less a functional description, not directly related to testing, but for the sake of completeness, basically I will describe you the circuit. So if you look at it, so there is basically, let me zoom it for you. So there is basically one subtractor involved. So the subtractor will do V1 minus V2. If this multiplexer select 5, 6 line is basically equal to 0. So it will be V1 will coming over here and V2 will be coming over here. So answer will be V1 minus V2. If the select line is 1, then V2 will be coming from here and V1 will be coming from here to the multiplexer. So it will be if it is a 1, it will be V2 minus V1, right? Similarly, this is a subtractor. Again, if you look at this part of the circuit, so there is a storage unit. This is your registers, where you store the values of variable V1 and V2. Of course, you require two comparators, whether both the numbers are equal or not, or whether whoever is greater than or greater than. So this greater than signal basically will be feeding these select lines. So as I told you, if V1 is less than V2, if this is true, it may generate the value 1. So then if it is generating the value 1, so it will be actually giving this value V2 over here and V1 over here. That is, if this is a 1, so this one is a 1, so this one will go over here and this one will be, so this one will be going over here. So it one will be V2 minus V1, it will be V2 minus. Similarly, the other way, if this is 0, so this one will be V1 minus V2. You can easily look at the first part of the circuit and you will be explained. And basically if you look at it, this is the storage part, initially you will be loading it. How will you load it initially? So if you look at it, this is the input line, this is your input line. So initially select 3, 4 is equal to, initially this will be equal to 0, initially. So initially if it is 0, so basically in1 will be coming to here. I will also make select 1 equal to 0. I will also make select 2 equal to 0. Sorry, I can make select 1 equal to 1, sorry. I will make this as 1 and I will make this as 1. And initially this is 0. So what is the case? So if it is 0, this in1 will be coming over here, it's 1, so it will be going over, it will be stored in register A. Again this is 0, so this one will be coming over here, this is a 1, so V2 will be storing in register B. This corresponds to this statement, initial statement. Again, this comparator business already I have explained you, that depending on this value, how this part of the circuit is going to generate these answers. Again, and there will be one more thing which is very important, that this, if you look at this point, V1 is assigned to V1 and V2 is assigned to V2. So if I make select 1 equal to 0 and select 2 equal to 0, the values of the variables are freezed. That is, they are not changed, because in one case it is V2 minus V1, another case it is V1 minus V2. So when this operation is happening, so V1 should be freezed and vice versa. So this part of the circuit, that if select 1 equal to 0 and select 2 equal to 0, you see that this is a feedback. So V2 is basically getting as a feedback from here. So they are basically freezing the lines. So these are design principle. You can easily look at this circuit and you can easily get a feel that how this circuit will be operating. Important point. So these lines, basically the select lines are control lines. There is actually a controller circuit which I have not shown over here. They will take the lines from here and here and they will respectively generate the control signals. Generally that is a small finite state machine for which you can use any way of testing, like use a Stackett fault model. But generally this is actually the data path. So data path testing is very complex. Why? because the number of bits like V1 and V2 may not be a single bit number. They can be 128 bit number, they can be 256 bit numbers, because you are computing the GCD of two integers. So integers can be long ints, they can be even floats, so it's quite large. So you have to appreciate that these bits or this mark size or this subtractor size or this register size are not single bit. They can be 256 bit registers, they can be a 256 multiplexer, they can be a 250 bit subtractor. So you can understand how large this circuit will be. A single multiplexer has some kind of 4 or 5 gates. A 256 bit multiplexer will have some 256 into 4 number of gates. Think about the subtractor. Subtractor will have very large gate if it is a 256 bit subtractor. And this is one small module of the ALU which can do GCD. So if the ALU is 128 bit ALU, or it can support 256 bit numbers, the data path which requires the mathematical computation becomes very large in circuit because of the increase in the data width. But these controller bits are always single bits, because they are taking some letter less than greater than signals and they are just sending out the control values as the signals. So it is nothing but a single finite state machine or a controller which will take some of the output bits which are generally single bit patterns, like less than signal 1, greater than signal become 1, and they will respectively control the select lines of the multiplexers. Generally it happens that way. So you can easily appreciate that this is a very small circuit. So for this, people are not worried about how to test it. Testing it very simple, you can take a single stacked fault model and go for structural test. But people are mainly bothered at testing of the embedded hardware because of the large precision numbers which are considering such multiplexers or which is part of the data path. So we will today see how to test this data path using software motivated fault models and testing at a higher level of abstraction. And again emphasizing, this is possible in embedded systems mainly because embedded designs mainly start from a software hardware co-design. So we will always have software specific models. Again, for this is again a design principle. I am not going into too much details on it, just I will give you the idea that how the control path works. So as I told you, this is the control path states. So Q0 may be the initial state. So as already discussed, that the initial state basically what should happen? The initial state basically should load this in value to register 1 and in value 2 to register B. So what it should happen? Sorry, it should have 0 because it should flow in, and select 1 should be 1 and select should be 1, right, and there it should be loaded over here. So in state Q0 basically we are saying there is some reset line which will actually be resetting the whole stuff. So that is the condition, and don't care less than or next this two greater than, less than, not equal to, not important, so we are putting DD. So if reset equal to 1, the next state will be Q1 because this is the Q0 is the reset state. From here you are going to Q1 where some functionalities will happen. But in Q1, what are the control signals generated? Control signal generated as cell equal to 1 and select 2 equal to 1. So it is going to make this as 1 and this as 1, and select 3, 4 should be 0. So sorry, means select 3, 4 basically in this case should be 0, right? So select 3, 4 is 0. So this is 0. So basically it will be fed over here, this one is fed over here, and this select 5, 6 is basically a don't care because I am not bothering any computation right now. That is basically your initial state. Next state automatically it will go to something called a Q2. Sorry, it will go to Q1. So if you look at Q1, so this is about your basically first state. Now in the state Q1, if you look at, there are two parts of Q1. So now you have to make this reset equal to 0 because work has started, computation has started. Now in Q1 there can be two conditions, basically not equal to either Q1, that is V1 is equal to V2 or V1 is not equal to V2. That is the condition that is being checked. At this time later than, greater than, equal to, I am not checking. This is basically corresponding to this line of code, right. So now if you look at it, so if it is not equal to, you are going to something to state Q2, because in Q2 it is, if you look at not equal to, you are going to state Q2, and in Q2 you will be doing all this comparison etc, right. And if it is equal to, that is corresponding to this, then basically you will be landing in the state Q1 itself. It will be the Q1 itself, that is already equal to. So basically you have to freeze the answer. So this is your answer, as if you look at it, this is your answer, output equal to V1 if V1 is equal to V2. So if you look at it, so it will go to state Q2, and in this case basically select equal to 1 equal to 0 and both are equal to 0 0. So you have to make all of them 0 0. So select 1 will be 0 and select 2 will be 0, right. So this one is going over here and this one is going over here, and we don't much bother about select 5 6 in the state Q2. I mean we can analyze this later on, right. And in fact in this case if both of them are equal, you will be going to state, you will remain in case state Q1 itself, and the answers are 0, 0. So basically in both the cases, if you look at, the select 1 and select 2 lines are 0, 0 in state Q1. So what is that? This is 0, 0 and this is 0, 0. This corresponding to the fact that V1 and V2 are freezed. There are no changes in value. But if it is greater than, if it is not equal to, if V1 is not equal to V2, then you are going to the next state where a lot of activities will be there. But if you are both of them are equal to, you will be in the state Q1 itself. So you will be here is a self loop and the value is freezed. So that is actually you have stopped over here, and the output you can take from the V1. But if it is not the case, so you will go to state Q2. That is this functional state you are going. They are not equal to. So again there will be 2 Q2s. Right, then again 2 Q2s. So in this case again, mainly I will be looking at the less than greater than, because in state Q1 I have already established that either they are equal or not equal. That was my main concern. In the next state Q2, my main concern will be less than or greater than. So in one case, if V1 is greater than V2, it will go to some state, and if the other case, it will go to a new state Q4. So there will be a bifurcation, and there will be going to state Q3 or state Q4, and in both of them the activities will be different. So if I start looking at state Q3, say, so in Q3 you will look at it, you will see that select 1 is equal to 1 and select 2 equal 0, and this one is a 1. So it is 0. So this one is 0. This is 0, and basically this one is a 1. So in this case, the V1 is freezed, and in this case the new value of V1 will be coming out. That will be nothing. That will be nothing now, right? So in this case, basically, so in this state, if you look at, we are looking at the state. We are looking at in Q3. We are looking at the basic case is this one, that is 0 and a 1 as the output. So in this case, if you look at, so this one is V1 is freezed and V2 is going to get a new value because select 2 is a 1. Now you have to be very much concerned about these two signals, 3, 4 equal to 1 and 5, 6 equal to 1. So 3, 4 equal to 1 and 5, 6 equal to 1. So 5, 6 equal to 1 means V2, and this one is, sorry, this is also 1. So it will be V2 minus V1, and this is also equal to 1. That means this one is going to be fed to this. So V2 is now going to get the value of V2 minus V1. And why it was so, because of the fact, it was so because if you look at it, so this is the case we are analyzing. So in this case, V2 was greater than V2. Just simple digital electronics. I am just given you the highlights of how it can be analyzed. So you can easily trace out the signals and the next state and the graph, and you can easily trace how basically this whole functionality will work. That is not the main emphasis of this course, to understand the working of this circuit. Just somehow I have elaborated for your understanding of the context of this lecture. Important part is, you have to understand that this one is a very simple hardware. If you try to implement as a circuit, this one will be some 10 or 20 gates will be there involved, irrespective of the bit size of V1 and V2. Say V1 is 128 bit, 256 bit. Circuit of this data path will be changing entirely, because it requires subtractor of high bits, comparator of high bits, less than equal to comparator of a higher bit orders. But irrespective of the bit size, these two tables, the control path will be always same, maybe at 10 or 20 gates. So testing this controller is not at all a concern for embedded system. Mainly I will be looking at testing the high level data path. So I have to do it at a higher level of abstraction. So as already told, that fault model is a very convenient way of representation. A fault model is reliable if there is a good correlation between physical defects and the circuit faults. So we all know that stacked faults are very good correlation with transistor faults, or transistor level faults, or physical defects, already well established. Now next reliable fault model, because it is said that the transistor level faults are reliable, physical level faults very reliable, gate level and transistor level are somewhat correlated. So gate level are also very good, like stacked fault model is a gate level fault model. People have already established very well this concept using statistics, but still now not very good results have been could be established or statistically found that some more higher abstraction level of faults can be taken into picture. But recently some works have been coming out, and very recent concept has come out, in which case people have tried thinking fault models like this is defect, physical defect, then transistor, then gate, and then people are thinking at the RTL or software level. Then people have found out that this path is already established. Now still people are in the flow saying that we already know that RTL and gate level are quite related, because RTL is transfer level and gate level is this next level. So people have established that there can be a good correlation at this level theoretically, and still the research is on that how much correlation exists between RTL and physical defects. People have lot of statistical measures are still going on, and still the research is on to find out what is the correlation level. But still people have an estimate that as RTL has very good correlationship with gate and gate has very good correlation with defects, so there should be a very good correlation. But people are still prone, we have to still use RTL, because I cannot go for gate level, even if gate level is very good and very reliable, but for large embedded system, gate level fault modeling is not a very good practice because of the complexity involved. So even if I know that gate level is very good, but because of the large side of the circuit I cannot go. So the current research is that whether we can apply any RTL level fault models and test this testing at a higher level of abstraction, and if it is so, how much good the correlation is. So, but the next generation testing will always be at the higher level. However good is the Stackett fault model and the gate level, we cannot go for the complexity. So let us see how it gets modified. So fault models in case of RTL are at the highest level of abstraction, directly as like your software programming. So, and the fault models are such that you can insert them at the RTL. Of course, you cannot have Stackett fault model and insert at the RTL level. That is not going to be do any kind of logic solving, because RTL means you have if, then, else, like the code I have showed you, like this is the code. You can insert Stackett fault, like I can make all in equal to 0, but that is not at all going to solve the purpose, and people have seen that it has failed miserably, because if you are thinking a circuit in this level, the fault model also should be in sync with it. So the fault models are at the highest level, and they are injected at the RTL level itself, like Stackett fault models gate level injection. Here RTL level, high level faults are injected there, and they are mainly motivated from software engineering errors, or as I told you, it is very much feasible in embedded system, because embedded system design start with software. And people have really started finding out good correlation and good level. Of course, the correlation cannot be as high as 99.99%, but people have found out more than 90% coverage in this case. But the great gain is that you can save a lot in the complexity and the number of test patterns if you go at the RTL level. So with the increased complexity of circuits, people have to trade off that, because as I already told you, test industry is based on economics. So if the circuit size is large, you have to slightly compromise. There is no other way of doing it. So what are the important fault models at the RTL level? It's very similar to software engineering. Input, if input Stackett, that is the all inputs will be stacked or output will be stacked. Anyway, they are carrying that out, but there is only one of that. All others, lot of others has to be done, because first people tried that can I directly apply Stackett faults in RTL level. People failed miserably, but still they are into the picture. All inputs will be 0, all outputs will be 0. Apart from that, they are taking if stack fault, else stack fault, assignment fault, dead clause, micro operation, local data stack. Lot of these principles are from software engineering. I will give you an example, it will be becoming more concrete. This is the list. So I will take you an example. Input Stackett fault model. Like this is a code with no fault. This is primary input x comma y, this is the output. If some logical expression out is equal to 1, else out equal to 0. You can make all output as default 0. So this is the input and output Stackett fault model. Explicitly change the inputs and output to zeros. That is very simple, we are not much interested. If then stack fault. This is very important fault, not at all was present in structural fault models. If you look at it, it is more linked to the functionality of a circuit and more related to RTL level or software level. Such type of fault models basically first appeared in software engineering, because at that time we cannot call it as fault, basically it was a design mistake. But again the emphasis started again coming, or the motivation started coming from that fact. So what is the fault? If x logical expression then a equal to in 1, else if in 2. Let's go. Now there is a if stack, that is this is the only thing which is always going to be true, it will never come into else, that is actually if equal to true. That is the fault model. That was always tried in software engineering, because if you make certain errors in the coding, it may happen that you will never go to else. People start motivated from there, they have taken a fault model like this. If true, then this. Always true means you will never execute this. Similarly, assignment level fault. Some if then else are there, something is there, light equal to green, else light equal to yellow, else this. But in this case, what is the error? Instead of green, the assignment is different. So they are all software engineering faults, but still people try to incorporate them in the RTL design, and they have found out quite a good correlation with real defects. Although the motivation came from software engineering, the statistical results show that the correlation is not as high as 99% like Stuckett fault, but still about 90% correlation. But you can save a lot in the design fault generation time and the number of faults. So high level fault models. So in case of high level fault models, there does not exist any close correlation with the defects. So high level fault models are not considered very reliable, but it is verified that there exists good correlation between high level fault model and the gate level. Further, gate level fault models have good correlation with physical defects. So there exists indirect mapping between high level software based fault model and the physical defects, and people have found out approximately 80 to 90% correlation people have found out in most of the cases, and saving of complexity is very huge. So this is where you have to go in the next generation. If, as again repeating, if Stuckett fault may be very good, but still you cannot do anything about it because of the complexity. Now I will take an example. Again I will come back to the example of the GCD. So this is the normal behavior, and we are going to take a fault in a mux. So this is the normal behavior of the mux. If condition input 1, input 2, faulty behavior 1, they get swapped. So instead of 1 it will become 2 and 1. Constant input. For both the cases the output is input 1, and the second case the output is input 2. People have found out that if you take this fault model for a mux, then more than 95% plus correlation has been established for the multiplexer. This is a figure I have shown you. So in a single bit multiplexer, the number of gates are this many, 1, 2, 3, 4 gates are there, and if you look at it there will be 18 faults. But in the high level fault model, this multiplexer has only 4 faults. Now I will bring you to the real crux of it. Assuming that is 128 bit multiplexer, then how many? It will be straight 128 into 18 into 128 number of faults will be there, as simple as that. But you have to appreciate that for this mux at this RTL level, even if it is 128 bit, 256 bits, the number of faults will be just this 4. That is what is the driving factor of this RTL based or high level testing of embedded systems. So even with the rise in the number of bits, the number of faults, and if the number of faults are less, also the number of test patterns will be less, and that is where you are going to be the king. So as I again repeating that now test pattern generation time is important, but not as important as the number of test patterns, because number of test patterns are to be applied in all these chips which will be coming to the AT. So if you have less number of faults, of course there will be less number of patterns, very direct relation. So in this case you are actually double winner. Firstly, as the number of faults are getting reduced at the RTL level, so the test generation time will be less, and if the number of faults are less, the number of test patterns will be less. So you will be a big gain in overall. Problem is that the correlation. So people have found out it's not very bad. For the simple marks, more than 90% correlation has been obtained. For many general cases, around 85 to 90 or 80 to 90% correlation is there. But gain is time, huge reduction in time, and basically the very less number of test patterns. Because as I told you, we are mainly worried about the data path for this, because more the bit increase in the data path, the bit width of the multiplexer, the bit width of the adders, the bit width of the computing units will start becoming larger. Control design is not much of a concern, because even if the number of bit widths increase, the controller size more or less remains same, because they take some of the comparator values and they generate some signals which are to control the multiplexers. So the size of the controller more or less remains same. We are more concerned about the data path. Right? Now I am going to test you how to test this circuit. We are taking this circuit as this multiplexer as a failure multiplexer. So what I have to do, of course you know that this is a problem. So how the fault will be sensitized? Of course you should ensure that means you are taking a case where there is a swap of values or something. So it is very obvious that you cannot take V1 equal to V2. If V1 equal to V2, none of the fault will be detected. So first what you will do, because I have to put some values as V1 and V2, so they are also having a scan chain, so I will take the scan chain, and what I will try to do is that I will load the values of register A and register V such that V1 is not equal to V2. Of course you can very easily appreciate the fact that if you are taking V1 equal to V2, fault will not be sensitized. The fault taken is something like this one, like whatever be the case, you are going to get the same input at the output. This is the case, the same input will be coming at the output, that whatever will be the case, this one and this one will be very similar. We are always going to take the V2 as the output. This one is not going to be coming at the output. Whatever be the case, the V2 will always come at the marks. That is something like this. This is the fault model we are taking. This one. Always the input 2 will be coming at the output. So this whatever be the case, if you look at, so always the V2 will be coming over here. So, of course, if to sensitize the fault, V1 should not be equal to V2, very obvious. So, we are making this V1 is not equal to V2 and select line we are making as 0. So, what we are going to get, the output should be here, the output should be basically equal to, if I zoom it, the output should be V is 0. So, in this case basically V2 will be coming from, sorry, V2 is 0. So, V2 should be coming from here, and in this case basically as it is 0. So, V1 should have been coming from here. Yeah. So, right. So, in this case it should be V2, sorry, it should be V2 minus V1, but in this case due to swapping of the values of the multiplexers, basically from here also V2 is going to come, and here also the value of V2 should be coming from here. If you let me just look at the normal circuit, we just look at the normal operation, then it will be more clear. Normal, the normal behavior of the circuit, let us look at. So, if you look at it, it is V1 and V2, and this is V2 V1, okay, and we are saying that our case will be basically the select 5 6 will be 0. So, if the select 5 6 equal to 0, so it should be V1 minus V2 should be there, but actually the error which you are going to take as the V2 will also be coming out of here, V1 will not be going to come out because of the fault. So, you are going to get V2 minus V2 in the case of error, which is shown over here. So, this is the error, right. So, now you have looked at it. So, it is 0 and 0. So, V2 is again coming over here and V2 is coming over here. So, normal case if you look at here, it was V1 minus V2 the normal case, but because of the error it is V2 minus V2, we should be a 0. So, this is what is showing you the circuit. So, this is the first case, scan chain is done and you are going to give the value of this one is equal to 0. So, instead of V1 minus V2, it is basically V2 minus V2. This is of the swap. So, fault is sensitized. Now, we again decouple, we can connect the scan chain values. So, in this case if you look at this V2 minus V2, so this is where the value of fault I am propagating over here. Select 3 4 I make it as a 1, same ATPG principle. So, this value will be passed over here, the value will be passed over here, and I also make select line equal to 1. All others are don't care. I can do this because I am doing a standard ATPG based solution. So, first thing is that again I am repeating what I am doing. So, the fault of the multiplexer already I have discussed. So, generally it should be V1 minus V2, but it is becoming V2 minus V2 because of the error, because V2 is coming over here, although V1 should come over here. So, I have sensitized this fault by making F6 equal to 0. So, this became V2 minus V2, and I am also say making V1 because I am having a scan chain control. So, I am applying the value of V1 and V2 I can control. So, I am giving unequal values, the fault is sensitized. So, instead of V1 minus V2, the answer is 0 over here, the fault is scan chain is disabled. So, the value is propagated by this path. For this I have to make select 3 4 equal to 1 and select basically this one also has to select 1 has to be a 1 and select 3 4 also has to be a 1, as this is the path. So, now it will be last in the flip flop the scan chain register A, and you will get the value of the output, and again you are going to test the fault. Very simple. So, I am not going to concentrate more on the ATPG because already we have studied elaborately for stacked fault. Now, just we need to see what we have achieved. So, the number of RTL faults is some 19. If you are take for this circuit, for a practical circuit like this, we have considered some 8-bit inputs. The number of RTL faults were only 19. The stacked faults were 844 for a simple 8-bit GCD computer. Minimization of test pattern time and very less number of test patterns. Because the number of RTL faults 19 means in the worst case you will have only 19 patterns. Number of stacked faults is 844 means it will be a high number of test patterns. So, by using an RTL model for 8-bit GCD, you can see from this example that we have reduced test patterns and also reduced the test pattern generation time. But what are the costs we are paying? That is, accuracy is lower, and many other fault models like bridging and delay, which we will see later, are not covered by this, because stacked fault model is very good. It has lot of correlation with other advanced fault models. So, all these things we are losing, but still we should go for it. The answer is yes, because in the next generation embedded system hardware with multiple cores, nobody will have time to generate, because it is only for a single 8-bit process, 8-bit GCD you can think, and a processor will have hundreds of such GCD units. And the saving will be much higher if you are going for a RTL model with some lowering of accuracy. But in spite of this, you have to go for it. There is no other solution. So, this lecture we have tried to motivate that one very interesting fault model which is against the concept of structural test, but still it is coming into picture of embedded systems because most of the designs are in software. So, very easily you can have the software description of your system and you can put lot of software fault models and test patterns can be generated very similarly like in case of ATPG, like sensitize, propagate and justify approach. But the interesting thing we have seen over here is the interesting fault model which is motivated from software co-design. Thank you. And in the next class, as I told you, we will be trying to look at testing of embedded cores, the bus and the memories which are using the mainly embedded system design. Thank you.